Okay, hi everyone. I hope this video finds you well. So today we are going to talk about pointers, and before we talk about anything, just fire up the Visual Studio 2019 and create a new project, call it Sandbox 8, and keep this project in case you needed it for the exam review or something like that. So today's agenda, we are going to start with pointers, and we are going to create and use pointers, understand what are they, why do we need them, and then we are going to move to dynamic memory, how to create and use dynamic memory, how to delete dynamic memory, and what do we mean by deleting dynamic memory. And finally, we are going to conclude this lecture with C strings. Those are the strings in old C, how to create them, how to use them. So I want to start with one thing that you should understand everything in this lecture, because understanding is more important than memorizing. Understanding lasts for a lifetime, memorizing lasts for a couple of weeks or maybe a month, but the most important thing is for you to understand this lecture. So something to think about as if we have a variable of type int and we stored 5 in that variable, like this. So when the variable is being created, what happens? So the answer to that is 1, memory is set aside. Set aside means reserved. And then the name num is associated with the memory location. And finally, we store the 5 in that memory location that is associated with the name num. Okay, now when is the memory requested? Or as the program is running, could we change the variable to hold more elements? Now, the memory is requested at runtime, but it's set aside or decided at compile time. So the answer to this question, could we change the variable to hold more elements, is definitely no, because it's being set aside at compile time. After you run your program, you cannot change the variable to hold more elements. Now, the main benefit of pointers is that we will be able to ask for memory at runtime. So with pointers, we are going to accomplish the goal of this question: can we change the variable to hold more elements? Now, first, we will start with the basic concepts of pointers and what do we mean by a pointer. So a pointer is a variable that stores the memory address of another variable. So the pointer is a variable that stores the address, the memory address of another variable. It's something similar to references, but it's not the same. And we are going to kind of spend today's lecture on seeing how it's not the same. So here we have int num equal 5, regular variable. We didn't do anything new. And when we look at this variable, we are going to first ask for memory. The operating system gave us this location, and then we are going to associate it with the num name, and then we are going to store 5. Now then, here comes the pointer. We are going to create a pointer. The way we create a pointer is you need a data type, then the asterisk, which is the most important thing in today's lecture, the asterisk, then a variable name. Whatever name you choose, we chose int ptr, int pointer. Now that defines int pointer and give it nothing. So basically what's inside of here is garbage value, which we are going to change in a second. So now we are going to make that pointer pointing to num. How do we do that? We say int ptr, and we do not include the asterisk when we do the equal, when we do the assignment. And then we use ampersand, which means the address of num, the address of your variable. So basically what I'm doing in this line is saying, since the int ptr is a pointer which stores addresses, I'm going to store the address of num. This is how I ask for the address of using the ampersand, and address of which variable? Num. So this is the address of num, right? So that is being stored in here. So if I print int ptr, I'm going to print the address, which is the 2000, right? The address stored inside. So basically, whenever I print, I show or display the contents of a memory location. The contents of memory location, like this one, this is 2000. And when I print asterisk in ptr, I'm dereferencing. Remember, this is basically now referencing num. So I'm dereferencing what the pointer is pointing to, which means I'm accessing what this memory location holds. So basically I'm printing the 5. Dereferencing the pointer, which means where the pointer is pointing at, which is here, print the content of that memory location, and that prints 5. Okay, so basically, when I use the asterisk in defining a pointer, this is used for the purpose of definition of the pointer. This is how I tell the compiler this is a pointer. But if I'm using that attaching to pointer with assignment, with something like this one, insertion operator, this is basically I'm saying dereference the pointer. Dereference the pointer. So here's how I create a pointer, and here's how I dereference a pointer. So if I'm going to change the value of num using the pointer, I'm going to dereference the pointer, then assign it with the new value. And now this outputs 6 if I printed num, because remember, this is pointing at num. It's like if we have a box and I can change the value. This is me. I'm changing the value. Then I give you privileges. I'm giving you privileges using these two sentences. Now me, num, and you being the int ptr. Now I give you privileges to change and to see what's inside the box. So I put $5, and you can come in here and see what's inside the $5 if you want to use it. And if you want to put more, extra $1, that makes it $6. So asterisk in ptr to dereference the pointer, that returns a reference to num. Okay, so here it is. Here it is. Now this creates a num variable. It's of type int. We store 5. Then we create a pointer that points to num using the address of. Then we dereference the pointer and assign it the new value 6. When you printed what's in num, printed the 6. Here is the total summary of all this. Now, here is something. Now, with reference variables, if you remember, you cannot reference another variable with the same reference. But in pointers, you can. In pointers, you can. So basically, if I have this, int num equal 5, int asterisk int ptr, and then I say, okay, int ptr is pointing to num, which is something like this, right? Then I print the address of num. This is going to print the address of num, which is the 2000. Address and num, this is printing the 5. So you take this code, the whole code, and put it in your Visual Studio and try it. It's not going to print 2000 because it's going to be different for every one of us, right? Even for you, when you try your code twice on the same machine, on the same project, it's going to give you different addresses. So if I print int ptr, it's going to print the 2008. Those are kind of presumptive numbers. So those are hypotheticals. It's not real numbers. So asterisk ptr, this is dereferencing the int ptr, and this is printing the content of num, because this is pointing at num. So printing 5, and then I change the value of num using or via int ptr and to 6, and then that prints 6, and this is printing 6, and this is printing 6. So let me just do this quickly, and I show you what I mean by 2000 and 2008 are hypotheticals. So I'm just going to take this and put it inside my Visual Studio. Let me just run it. Oh, first I have to change these because the compiler is not going to recognize them. So changing these, the compiler now recognizes this code. So here it is. The first time we printed num was 5, and then we printed int ptr, which is the memory address. Let's get rid of this one. Memory address, and then we have asterisk int ptr, which is the 5, as we said. Then we assign a new value to num via int ptr. We have 6, and here in num, and cout num and int ptr asterisk int ptr, which means dereferencing the pointer, and this is going to give you 6 and 6. Okay, so going back to our lecture. So this is interesting, but not very useful at this point. It's kind of like the first take on the reference variables, right? First we said, okay, that's cool, but why do we need them? Yeah, it turns out we need them for functions mostly, right? So, and for passing by reference. So, the different uses of asterisk. What do we know of? We have 3 usages, right? So create a pointer variable like this. And to get what the pointer is pointing at, dereferencing the pointer like this. And as the multiplication operation. Num equal 24 times sum num. So the compiler now is going to deal with this as the multiplication. How can the compiler tell them apart? Basically by the position of each asterisk. So if the asterisk come in between a data type and a variable, this is creating a pointer. If it's before the variable, like int ptr in this case, and it's involved in assignment, printing like couting or insertion operator, or something like that, or even something like that, depending on the position, it's going to count that as dereference. And if it's something doing 24 times some num, something like that is going to find it to count it as multiplication. But if you have something like this, 24 times asterisk num, it's going to try to dereference this one in some compilers, and some compilers are going to give you error because it's confused. That compiler is going to be confused. So it's always better if you're using something like that, it's better to have it in parentheses. So how many different ways can we use the ampersand? To create a reference variable like this. And remember, with reference variable, you must give it the variable to refer to at creation time. In pointers, you don't have to. You can do something like this. Then later on, you give it a variable to refer to. So the second use of ampersand is being the address of. And don't forget the logical and. The logical and in Boolean expressions, right? How can the compiler tell them apart? Same way, based on the positioning of the ampersand. Okay, the syntax of creating a pointer. Now we can create initialized pointer or uninitialized pointer. Uninitialized pointer is just defining the pointer without giving it a variable to refer to. So, or to point to, not refer to point to. So int asterisk IPTR, so IPTR is now a pointer to an int, but which int variable? Not yet defined. Same thing in here, but to a character. Example of initialized pointer, you have int I equal 1, character C equal Y, and then you give it, when you create the pointer, you give it a variable to refer to. This refers, this PTR refers to I. This T refers to C. So, some students ask, okay, where should I place the ampersand? Is it next to the variable name, like the pointer name, or the data type? Now, basically, the compiler doesn't care, but some programmers do, and there is a reason why they do. Here's why. So answer me, how many pointers do you see in this statement? Now, some of you would say, okay, it's of type int asterisk, so I have 2 pointers because I want them to be pointers. Even the naming, it's kind of saying that IPTR and IPTR2. But actually, what we have is IPTR as a pointer, and this is an int variable. This is an int variable. So this is not a pointer. So how do we make it a pointer? By placing another asterisk before this name. So this is not much of a problem because modern programming styles saying do not create pointers on the same line with normal variables. So if you intended to have 2 pointers, you have to do it this way. But if you intended to have 1 pointer and 1 variable, like normal variable, have them both in separate statements, separate lines, based on this style or standard. Okay, so the address of operator. More example of using the address of operator. So int I equal 1, int j equal 2, int asterisk ptr, so we are creating a pointer, and then we are saying, okay, ptr is pointing at I. And remember, when you point a pointer to a variable, you do not have the asterisk. You don't have the asterisk. So we just say ptr equal the address of I, and you must have the address of, right? It's not like reference variables, so you must have the address of operator. Then, if you want to change the value of I via ptr, you dereference the PTR, so you access the content of that variable, right? Then you change it. 3. Same thing when we do that with J. And remember, with pointers, you can make the same pointer pointing at one variable, then pointing at the other. You cannot have one pointer pointing at two variables, but you can reuse your variable, your pointer variable. So when I print I and J, I print 3 and 4 because I changed them via PTR. Okay, so revisiting the swap function. So swap function using reference parameters like this, right? We have seen this before. So everything was working perfectly, and when you used it, you just gave it A and B. So what happens if I'm going to change these to pointers? So changing them to pointers, and this is actually how it's being made in C programming. It's in the old C. So you do pointer PTR1, another pointer PTR2. Now you create a character if you're swapping characters as a temp. Then you dereference PTR1, put it in C. Then dereference PTR1 and put the dereferenced value of PTR2. And PTR2 now is not usable. I didn't want to say empty, not usable. Or the value inside is stored somewhere, which is in here. So now you can say asterisk PTR2, which is storing what's in C in where the PTR2 is pointing at. But wait a second. It's not finished yet. When you use the swap, since those are pointers, you must provide them with addresses. So you have to give it address of A and address of B, because what you're doing in here and in here and here and in here is dereferencing those addresses, right? Dereferencing those addresses. So sort function. Same example or same exercise I gave you in reference lecture, right? So you have you use a sort function, create a sort function that has 3 in pointers, not 3 references like last time. Change the references to pointers, and inside your sort function you will put a smallest number in n1 or num1, the next smallest number in n2 or num2, and the largest in num3 or num3. So C++ has a built-in swap function that you could use. It's a function prototype. A prototype looks like this. You can use it, or you can use the reference. So take 5 minutes. Try to do this. Here's your main. Copy this to your main. It's asking the user for 3 numbers. The user is going to enter those 3 numbers, and you sort them using your function. And remember, we give it address of, so we are given in the function addresses, so it must be of pointer parameters, and then print them, which is going to sort them and print them this way. So take 5 minutes to do that. Pause the video, do it, and then come back to see the answer. Okay, assuming you came back to see the answer, here is the answer. So sort function that takes 3 pointers, and when we are going to compare, we compare the values, so do not forget the asterisks. And we swap the values, not the addresses, so all with asterisks, right? All with asterisks. Okay, so reference versus pointers. Reference variables can only be assigned or initialized at creation time. So if you have variable int num equal 5, num2 equals 7, and when you create a reference int ampersand ref, which is creating a reference, you just give it num. You just give it the variable, not the address of a variable. But if you create a pointer we store addresses inside. So you give it address of num. So later, PTR can be changed to point to num2, but ref cannot. So ref, once it's pointed at, referred to a variable, it cannot be referring to another variable anymore, any other variable. But with pointer, you can reuse the pointer. So 2, reference variable can be used like a normal variable, doesn't need to be dereferenced, but a pointer must be dereferenced. So if you are using ref in here, you can just say ref equals 6, and then ref is going to change num from 5 to 6. And if your now PTR is pointing at num2, when we do asterisk PTR equal 8, num2 value is going to be changing to 8. Num2 value is being changed to 8. Here it is. Okay, so if we have something like this, int asterisk int PTR, and we dereference the int PTR and put 42, what do you think this will do? Now I want you to notice something before you answer. We did not make this pointer to point to anything. What do you think it's going to do? So the answer is, it's a compilation error. It's going to give you uninitialized local variable int PTR used. However, in some older compilers, it's going to try to dereference the garbage value in here. Remember, in C++, whenever you create a variable or a pointer variable or any kind of variable, basically that memory location holds garbage value until you change it, right? Older variables or older compilers are going to try to dereference the value in here and then store 42 in that location that is being pointed at by garbage value in here. Okay, so today I'm introducing null PTR to you. So null PTR, basically it's address 0. So if you have a memory, the first address in your memory is basically the address 0. Remember that we start with 0. So address 0 is empty. Basically, this is the memory location that is empty forever. Why? Because we want to say that if we use, for example, null PTR, which is pointing at address 0, that we are pointing to nothing. So this is used to indicate that a pointer is not pointing to valid data if it's equal null PTR. So good programming practice, something you get used to, is whenever you have unused pointers, you set them equal to null PTR. So a pointer set to null PTR will return false if used as a Boolean expression. Something like this. If I have a pointer and said, okay, that pointer is point to this location, which is a 0, meaning that it points to not valid data or pointing to nothing, which is the same thing. If I use it as a Boolean expression, it's going to give me false, like this. If you change something in here and pointer now PTR is pointing at valid data, it's going to dereference that data inside, right? So if you use null_ptr, this is going to give you false. So null_ptr, if used in a Boolean expression, giving you false. It's good information to know. Okay, so going back to what we have a couple minutes ago. So if I do int asterisk and ptr, and my pointer right now is pointing to null_ptr, and I try to dereference null_ptr to store something, it's going to dereference the nothing, which is basically, remember, why do I say nothing stored in here? Because when you try to dereference the nothing, like it's air, right? Nothing to dereference. So now every compiler on Earth is going to give you a compilation error because you're trying, there's actually no garbage value to dereference to begin with, right? Okay, so before C++ 11, like in C++ 9 and before, 0 or null was used to represent the empty or the null address. The problem is that null, the word null, was defined in many libraries and had different meanings. So if you're using many libraries and it happens that null in one library means 0 and null in another library means something else, it's going to confuse the compiler. So it's always better to use null_ptr. Now, if you use 0, this will work. This will work. But null_ptr is going to be a better and more clear solution. So int asterisk ptr equals 0, then dereferencing the 0, it's going to give you an exception. Exception, basically a runtime error. So with pointers, you are able to change two pieces of data. Which variable the pointer is pointing to, which means the address, so you can reuse the pointer, and you can also change the value of the variable being pointed to. Now, if we have character C stores the lowercase c letter, and same thing with E, pointing, this is storing lowercase e, the letter, and we have a pointer ptr1 of type character that points to C, to this variable, and then I try to dereference ptr and store the uppercase C. This is changing the value to C, so initializing to point to 1. Here is the first case, which is this one, and then the second case changing the value is this one. And I can reuse the pointer to point to E, to this variable now. And I can change the value of E from lowercase to uppercase. Right? Okay, so we have something called constant pointer. A constant pointer is a pointer that cannot change to point to a different variable. So basically, right now, my pointer is similar to reference variable, right? Because you can change the data inside that variable you're pointing to, but that pointer cannot point to another variable. So character C equal C, and same thing with E pointing, storing E. Then character asterisk const ptr, so the constant part is the pointer. The pointer cannot point to anything else. Now it's pointing to C. You cannot point to any other thing than C. The first thing that points at is constant. So asterisk ptr, you can change the data inside, because the constant is the pointer. When you try to change the pointer to point to E, this is going to throw an error. Also, we have a pointer to a constant data. So the word const comes before the data. So depending on where you place the word const, if it's before the pointer name, then the pointer is the constant, which means the pointer cannot point to anything else. If you placed it before the data type, then the value inside is the constant part. But you can point to another variable. So if ptr2 is pointing to d, this d variable, and you try to change the data inside, it's going to throw you an error. But if you try to use ptr to point to e, then this is legal. This is okay. But trying to change the variable, to the data inside, this is what's illegal. So we have 4 types of pointers. 1, the regular pointers without any constant involved, right? So, can point to different data? Yes. There's no constant. So yes. Can change the data pointed at? Yes. Because there is no constants. Okay. Now we have the word const. Or let me just underline the word const. We have the word const. Now, const IPDR can point to different data? No. But can we change the value inside? Yes. If const comes before the data type. Can we change the value inside? No. Can we point to a different data? Yes. If we have const before the data type and const before the pointer name, then you cannot point to different data and you cannot change the data inside. So if you read it from left to right, you know what that means. So int asterisk const IPDR. Okay, const IPDR. So this is const pointer. Const int. Okay, I know now. Const data. And not const IPDR. And so on. Okay. So try this in your Visual Studio and come back to continue this video. Okay. So why do we use pointers? Seem like a lot of trouble, and why do we gain by using pointers? Because we have alternative, we have reference variables. That is correct, but pointers are going to give us something we are going to see for the first time, and something very useful. The big benefit of pointers is that you can ask for memory while the program is running. So, for example, I can ask the user for how many students do you have in the class. The user enters something. Then I say, okay, if that is being greater than 0, if you entered, for example, 100, 1,000, 1,300, whatever that is, then I can ask for memory at runtime. Where do I ask this memory from? Where do I ask for this memory from? The dynamic memory. The dynamic memory. So, you used to have arrays that are fixed, right? Arrays that are fixed. Today, we are going to see that we can have dynamic arrays, which means that I can ask for the size of the array at runtime from the user. Remember, regular array or normal array, an array that can use a size that is either literal or constant. Today, we are going to be able to use a size from a user input, for example, or a variable. This is what's called dynamic memory. So dynamic memory is the memory that is requested during a runtime while the program is actually executing, and we ask for it using the new keyword, the new command. There is another term that is called dynamic allocation. Basically, this is the process of giving of the memory during the execution of the program. So memory for dynamic variables. So this is requested from the heap, which is a data structure that is used by our program. Some people also call the heap the free store. So if there is enough memory to satisfy the request, a pointer to that memory is returned by the operation. And we are going to see how. If the operation is not enough, if there is not enough memory to satisfy the request, an exception is generated. As I said, an exception is an error message which is not, if not handled or corrected, it causes the program to terminate. Basically, it's a runtime error. More on this next core in CS132. So in old compilers, an exception is not going to be generated. However, they were actually returning 0 if there is no enough memory to satisfy the request. Okay, the differences between local variables and dynamic memory. So in local variables memory is acquired automatically and is being returned automatically when it goes out of scope. In dynamic memory, you have to ask for it using the new command or the new keyword. And if the pointer that is storing the address of that memory location in the heap goes beyond the scope, it's still being allocated. It's not being returned. To return it, you have to use the delete operation or the delete keyword. This is what we call deallocation request. So asking for the memory is called the allocation, and returning the memory is called the deallocation. Okay, here's an example that will make things clear. So if we have a function that takes a normal variable, num, and defines another variable called zip equal 5 of type int, and a pointer, int pointer, that stores 12 in the memory location in the heap. Okay, here's how it works. When we see an U, we know we are dealing with the heap. So to be able to store the address, what do we use to store addresses? Pointers. So create a pointer IPDR, and then ask for memory location to store the 42. Then you're asking, using the new keyword, you are asking the operating system, do you have a memory location that I can store 42 inside? If there is, the operating system is going to respond to you and give you an address. So you store the address in IPTR. If there's not enough memory and there's no memory location for you to use, the compiler is going to produce an exception. Okay, so we asked for memory, the compiler and the operating system satisfied our request and give us a memory location. So now IPDR is pointing at something in the heap and we store 42 inside. Then we pass the value, which is the 42. We dereference that pointer, so we are asking 42. So 42, and again, when we use new, only you store things in the heap. So we are dereferencing IPAR, which is we are actually accessing the 42 and pass the 42 to foo. So num now is holding 42, the value. So basically num is not pointing at 42. No, it stores 42. It's like I give you a replica of my $5, right? That's it. So I have $5. I store it in the bank, in the heap. And I go inside my deposit box in the bank. And I copy that 42 and give it to you. I have 42 bucks inside my box. I go copy the 42 bucks and give it to you to store it in your pocket. And I'm referring to pocket, your pocket, as a local variable in the stack, and the bank as the heap. Okay, so int asterisk PDR equal new int 12, and I have a very normal variable stores 5, and then a PDR storing 12 in the heap. Now, if we finish executing statements in this function, usually every local variable goes away without even my intervention, because the garbage collector is collecting unused variable, or basically the variables that go out of scope. So the garbage collector is basically removing the whole stack frame, right? Stack frame with all its local variables. So this is a local variable, remember. Yes, it's a pointer. It points at something in the heap, but it's basically a local variable, like zip. So a pointer is a local variable. It's always a local variable. But what concerns us is that now we have something in the heap we did not return. Remember, you have to return using the delete operations, and we did not use anything. So, since this PDR is now deleted as a local variable, it's deleted, but 12 is not returned. So the operating system still thinks that you are using that location in the heap. This is what we call a memory leak. A memory leak is when the operating system thinks that you are using that location, while actually you do not have access to that location. You do not have access to that location. Same thing. It's if like you have a deposit box in the bank, you store your precious things in that deposit box, and then you lose your credentials. You lose your credentials. Now, it's still there. Your precious things is there, but you cannot access them because you don't have the proper key. So how the new command work? So the new command work is used to acquire memory from the heap. So if we do this int asterisk PDR, this is creating a pointer, then you ask by new, you ask for one location, for example, or multiple locations. We are going to see how we ask for multiple locations, like for array. So for one location, this is how it's used. For one location, you ask for one location, and if there is memory locations in the heap to satisfy the request, a pointer is returned, and you sort in PDR. So the newly acquired memory is uninitialized, contains garbage, right? Because you don't have anything, you don't initialize it. Like this. If you ask for an int size location in the memory, it's going to have something, but you don't know what is it, right? Something unknown, uninitialized. So IPDR on the stack is pointing at something in the heap, and you don't know what that is. But if used with a string, basically the string object with the default initialization is going to give you empty string, which is just two opening and closing double quotes, right? And this is your strpdr. This is for the uninitialized. You can initialize it with something immediately by giving it something inside the parentheses. Something like this, for example. And IPDR equal new, and you give it a value. So you know, don't deal with garbage values. You give it a value. So it's 10 for the IPDR, and for the strpdr, you give it amazing string object. Something like this. Okay, so pointers and arrays. Here's how we ask for multiple locations, or basically an array. So again, whether it's you're asking for one location like this or multiple locations like this, like an array. When I say multiple locations, I mean array. You're storing one address. Remember that with an array, it was just storing, you're saying array A, and that is storing only the first location, and then you jump to the second location by the thing you place in here, array of 1. This is the second location, array of 2. This is the third location, and so on, right? So here is some data type, whether your array is going to be of type double, int, or whatever you want. So PDR is a pointer of type sum data type, like this. You can replace this with double type or anything you substitute. And size is the number of elements of the type sum data type to be constructed, and that could be a variable, whether it's coming from user input, whatever that is. And you can still use indexing. You can still use indexing on a pointer, the same way you use it with array. But this only makes sense if you're pointing to an array, not if you're doing something like this. It has to be having those square brackets, right? Okay, here's how we ask for array in the heap. So, a pointer A, and we ask for 3 locations in the heap using the new command. So, this is going to give me 3 locations. Then we put 5 in A1, which is the second element. We put 5. And we are asking for 2 locations for strings. So S is going to be, this pointer is in the stack, but the data is in the heap, right? So you put Baz in as 0. Here is Baz, and the other one is empty string. That easy. Okay, so now to linking pointers to regular arrays. This is a regular array. How do we know it's a regular array? There is no new command, right? There is no new command. So this is basically a regular array. And now we are not talking about the heap. We are not talking about the heap. We are done talking about the heap. So const int array size equal 20, and we put array size in here, and it has to be either a literal value or a constant variable. Here's a constant variable. And then we are replicating, or basically duplicating the address and store in another variable. So we are copying the address where ARR is pointing at, and we put it in PDR. So now array stores the address of the start of the array. Remember that when we do this. Now let's say this is 20, array size 20. So it's going to create 20 elements, and array is going to be pointing at this one. Now when we do PDR, now PDR is going to be another pointer pointing at the same location, right? This is what we have done. That's it. So if array stores the address of the start of the array, then how does this work when we do array of x, and x is being an integer, equal 3? So this is exactly working like this. This is being behind the scenes as pointers. We are dereferencing this. What is this? The start location. Remember that we have something like this, and we do array pointing at the first location. The start location plus size of what type we have our data. We have int. Size of int, which is basically 4 bytes, times x. So if we have x being 2, then the first address, let's say that every rectangle here is 4 bytes. So 4 bytes, 4 bytes, 4 bytes, 4 bytes, 4 bytes, and so on. So dereferencing array this location plus size of int, which is like the 4 bytes, times x, 2. 2 times 4, basically this is 8. And this location plus 8. So you skip 4 and 4. So you're now pointing at this one. So array of 2, basically we're talking about the third element. 1, 2, third. This is how it works. This is how it works. Dereferencing, because we want to access this location and store the 3. Okay, so assuming that we have this example, same example, and we have pointer that points to array, so something like this again. Here is array, and I created ptr that points to the same location, to the first location in here. Now, assuming that we filled the array, I can then use ptr the way I used array before. Now we know array stores the address of the first location, right? ARR stores the address of the first location. Same thing with array. So I can use ptr with the square brackets, the way I used array before, right? Like in regular for loop. Something you used to use. Okay. I can also use arithmetic operations like the plus, plus, and minus, minus to move the pointer forward or backward. I dereference the pointer and print it. So I print where that pointer is pointing at. So array and ptr. And ptr is going to jump location by location, so the size of int in this case. So I dereference pointer, then I say okay, move. Dereference pointer, then I say move, and so on. So, or I can use it in the same statement, asterisk ptr plus plus. But wait a second. Which one has a higher precedence? Which one goes first? The plus plus or the asterisk? This or this? Now the answer to that is the plus plus has a higher precedence than the asterisk. So if that is the case, then you're saying that I advance first, then I do dereferencing. So basically this statement is not printing the first location because it advances first. Actually, no. How so? Is by knowing or by understanding how the ptr++ work. How far this will move. So we answered this that it will move the length of one of its data types. So if I have int array, then I jump int size, which is 4 bytes if the element's type is int. Now, how does the post increment operator do if the plus plus is just a function and ptr is passed to that function? So basically here is the function. It's a special function called operator function, and it's operator plus plus. It takes a pointer and it returns a pointer and does something inside. What it does inside is first making a copy of the address being passed, and then incrementing the original address by the size of int, and then returning the copy. And remember, now since we are talking about pointers, there is no passing by value or passing, so you are dealing with addresses. You're passing the address by value, which means the data inside, when you're doing something, you're doing that permanently. There is no replicas, right? Okay, so again, in asterisk PD operator plus plus, so we return the pointer. Pointer to what? We return the pointer to copy. So we do actually increment num by size of int, but what we return is a copy. This is why when we do this, we're not skipping the first location. No, we are not. And I'm going to prove it to you by this example. So here is the function. Keep an eye on that function. And here's an example. In array 3, 3 to 1. So we have 3 to 1. We made a pointer that points to array. So array and pointer both are pointing at 3 at this location. And here's an I. Here's I. I is going to go through 0, 1, and 2. Now I'm going to show you only what happens in one iteration, how that works. And this is the most important thing. Now we do asterisk PDR plus plus, how that works. So I'm doing plus plus, which means I'm using this function. What do I pass? I pass a pointer, num. So basically I'm passing PDR. So I'm passing PDR. Then 1, make a copy of that PDR where pointer PDR pointing at. So a copy now pointing at the same location because I'm passing the address PDR, right? And then I'm saying num plus equals size of int. So PDR is being num, right? PDR, because this is what I'm passing, is being substituted by num. Then I'm incrementing num by the size of int. So PDR is advancing 1 int, which means 4 bytes, 1 location. Then I did this. Now for the substitution, I'm returning copy. So copy is being returned, and copy is not moving, right? We're just doing a copy replica, right? So I'm returning the copy, which is the original position of PDR. Now, dereferencing the copy is going to print you 3, right? This is going to give you 3. And that's it. And that's it. So if you did not understand how this is actually happening, go rewind the video and watch it again. So create an int array of size 10 and use a for loop and an int pointer to make the values 1 to 10. Then use a for each loop to output the elements to the screen. And again, no square brackets allowed. So you're using the PDR, the plus plus, and the asterisk, right? The dereferencing operator. Okay, so pause the video, spend some time on it, and then return to the video and see the answer. Okay, here is the answer. We are creating int array of 10, and remember I didn't actually say heap or dynamic memory. If I didn't say dynamic memory, then you don't have to use the new keyword, right? So I'm creating 10 locations, array of 10 elements in the stack. This is an array in the stack. If I use the new, then that is going to be in the heap, and I didn't ask for this. So I'm creating another pointer, PDR, that points to array, same thing. And then I'm saying for int I equals 0, I less than 10, the size of my array, I plus plus, then I use asterisk PDR plus plus, and I store I plus 1, which is storing 1, 2, 3, 4, 5, up to 10. Then I'm using for each to print each element. Here's one solution, and remember, this is going first, for this one, it's going first to finish the right hand side, which is I plus 1, 0 plus 1 equal 1, then doing the thing in this function, making copy and moving the PDR, and then dereferencing the copy, and that's it. Here's an alternative solution. Same thing in here, but you can do asterisk PTR I plus I, and you remove the plus I from here, right? And then you advance the pointer. You advance the pointer. You advance the pointer. And this is going to be exactly doing the same thing. Okay, so remember from lecture 5 when I said, when we pass arrays, they're always passed by reference even without using the ampersand? That is actually true. That is actually true. And here is the reason why. But first, remember this example when we use sum array, when we use this nums with 4, this is summing 1, 2, 3, 4, giving you 10. Only the first two elements giving you 3. And when we do that, that was an error. And we said why? Because this receives an array, should receive an array, and you're sending one element, which is you're sending int. Okay, remember that? Now, this function is using an array parameter. Can we make it use a pointer? Yes. Why? Because behind the scenes, what you were passing when you're passing nums, now we know that nums storing only the address of the first element. You were passing the address. So this is why we are saying, oh, we were passing arrays by reference. So basically, we were passing the address by value. This is what actually happened. That acts the same as passing by reference. Same as passing by reference. Okay, so now what we are going to do is, since we are saying this is storing address, we are going to replace this with a pointer, something like this, constant int pointer. So when we say constant int, you cannot change the data pointing at by this pointer. You cannot change the data. You can use it this way, right? PTR I. So I didn't change anything. I just changed this. Something you just have learned. And you can also do this, right? Because this behind the scenes is this. Int asterisk const array. Const array, right? So array, this variable, cannot point to anything else. Same thing if we do this. And you can't change the data since there is no const, so there is no const. If you want to have const in here, then add const in here. That's it. That's it. So we could use an int pointer as the parameter, and it will work the same way it works if you have int array parameter. This, same thing, right? So if you want to do this, you can do this. If you want a constant, you add a constant. Now it's a piece of cake for you. Okay, so giving the memory back. So we give the memory back if we have used the new or this new. This is asking for one location. This is asking for array, multiple locations. If you asked for one location, you just use delete and you give it the PTR. You delete the pointer. If you used new square brackets and used some size in here, you use delete. And when you delete, you do not specify the size. You just use delete. And I'm going to show you an example of how to do that. So storage pointed by the PTR and array PTR is returned to the heap. PTR and array PTR are now undefined. They still point to the old dynamic data, but that memory could be given out again. Which means that when you use delete, you can still have access to those locations, but those locations are not now storing your data. They may appear storing your data for a moment until the operating system gives them to another process, and then you're saying those are actually storing different data. So here's an example of using and cleaning up the dynamic variables. So we have size, ask for the size from the user. So assuming the size was like 10, then we ask for 10 locations, or basically array of 10 elements in the heap, and we stored the then operating system replied with the pointer or the address, and we stored it in the pointer. Then we used three functions: get list, we filled the array; sort, we sorted the array, and then we displayed the array. And then how to delete that? We deleted array PTR, so we use the pointer where we stored the address to delete, and we use delete and the square brackets. And something to notice that it's empty. We did not say delete size. No, we did not say that. Right? It's empty. Okay, so dangling pointer problems. Here's a problem of dangling pointers. What do I mean by dangling pointers? I mean that int asterisk a equal new int 5. For int I equals 0, for int I equals 0, I less than 5 plus I, a of I equal I, and then I created another pointer that points to a. So now I have two pointers pointing to the same locations in the heap. I can use either one, right? I can use either one. Now, memory leak is going to happen only in the heap. Because look at this one. Now if I do delete a, now I'm asking the compiler to give away or give back those locations to the operating system. So basically now I think I don't have access to those locations. Actually, you do have a pointer. This is the dangling pointer, a pointer that's still pointing at those locations, and those locations are going to be given to another process by the operating system. They may appear to work for a second or two, but then the operating system gives them to another process. Then another process is going to use them and store different data, right? But you still have a pointer that access them, because that pointer is storing the address of the first location in here, right? So you can have access using the I or X or whatever variable you use, right? Using the square brackets. Okay, another example of dangling pointers. So we have a pointer that point to int, another pointer that point to PTR. So basically we have two pointers pointing to the same locations. And then we deleted one of them. And then we said, okay, equals 0. Now we are putting PTR is storing null PTR, so you cannot dereference. And you think you give away the memory, but you still have other pointer dangling because it still has access to those. So we have a rule that set deleted pointers to 0, all null pointer, unless they are going out of scope immediately afterward. Unless they are going out of scope. When I say out of scope, I mean they're not pointing at anything in the heap. Okay, memory leak problem. And this is one of the biggest problems in C++, memory leaks. So if I have the same example, array, and then I say array equal new int 5. So basically I have array that points to 5 locations in the heap. Then I use this pointer to point to another. Those are totally new 5 elements. So those I did not give back to the operating system, and I use the pointer to point to another 5 locations. So that means the operating system still thinks that I'm using those while actually I don't have access to. And my pointer is pointing to something totally else. Okay. So basically, memory leak is when the operating system thinks that I'm using memory locations while actually I don't have access to them. Like this case. Or something like this. If I have, this is so dangerous, by the way, because this is still like thinking, okay, as long as the process exists and you did not delete or give back the memory locations, the operating system still thinks like you're using them. And this is consuming your memory without your knowing because of one single mistake. So something like this, if I have an asterisk array of 5 locations, so I ask for 5 locations in the heap. And then, when I give back the memory, I forget the square brackets. So I give back only the first one. And the operating system still thinks that I'm using those, while actually I do not have access to them. Because my array now gave this one. Or I actually do have access to them if I use them properly. But my intention was to give back the full array, and I only gave 1. This is one extra example of memory leak. So, we are going to conclude this lecture with the C's way of doing strings, or what we call C strings. So, strings in C are character arrays with \0 at the end. So, the \0 in ASCII is 0, which is also called null. And remember, with ASCII, like for A, the smaller A, we store 97. For uppercase A, we store 65, and so on. So, going back to the definition of the C string is a null terminated or ended character array. Null terminated character array. So, here it is. A character array. Then I ask the user for his or her name. Then I store it in a cin. So I can use cin and cout with character arrays because they are considered a C string, the way you use it with a regular string when you included the string library. So I use the insertion operator with C string, which is the character array. It works. Okay, here's an example of that. And if I'm going to print, for example, each character in my character array in a separate line, the way I'm going to do it, and when you actually, by the way, something worth mentioning, when the user enters something, when the user enters enter or presses enter, that actually going to append. So let's say that I said A, B, C, which is I inserted in here A, B, C. It's going to store A in the first location or the first element, B, then C, and I pressed enter. If I pressed enter, it's going to immediately add the terminator without me knowing. This is why when I print it, it's going to print. Now, if I want to print each of these A, B, C in separate lines, because this is what I entered, right? I don't know what happens behind the scenes, assuming that I'm a regular user. So, I'm going to print that using a while loop, and the while loop is going to use a pointer. I make a pointer to point to my array, the way I use it with regular array, int arrays, and so on. So, character pointer that points to CSTR. Here is A, B, C, and the asterisk. and sorry, the null pointer. This is CSTR, right? CSTR is pointing at this. Now CPTR is a pointer that points. CPTR is pointing at same location CSTR pointing at. Now I can do asterisk CPTR not equal the terminator, the null terminator, print that and advance the pointer. So that prints A. This is A, not D. This is printing A, then point at B. Same way with B, print B and point at C, print C and point at the \0, the null terminator. When I reach the null terminator, is the null terminator not equal to null terminator? False, so that goes out. This is how it's being used. Or since this means 0, right? And 0 means false, I can just use the asterisk CPTR, right? So with ABC, it's going to print A, B, C, and then this is 0. When we have 0 inside of here, it's false. Why false? That goes out. That's simple. Okay, so we have a function that finds the length of a string. So if I have Sam, S-A-M, and \0, it's going to return 3, right? Because if I give you Sam, and I say, how many characters do you have in here? You should say 3. Not saying 0, 1, 2, you say 2. No, you should return 3, the length. So how that works is that here's the function that returns the number, so it returns an int. And it takes a pointer to that array. So it actually defines int I outside because we are going to return I, the number of my characters. And it says I equals 0 as long as CPTR of I not equal the \0, or you can just do CPTR of I, right? Because again, it can be used as a Boolean expression. When it is \0, it's going to be 0. But okay, wait a second. We are going to see that in a different slide. So CPTR of I not equal the null terminator, I++. And here is empty loop. So we have a semicolon, which means empty loop, right? Empty loop. And then returns I. So A, B, C, A++. So we start A with ++, B++, C++. So now we have 3. And when we have \0, choose the null terminator, this is false, and this returns I, which is 3. So what does strlen need to work? That your string is terminated with a null terminator, the \0, right? Your string must be null terminated for this to work, or actually for all C string functions. Now you can use strlen in your Visual Studio, but you need to include C string. You can use, for example, strlen, something like this. You can take this code and put it in your Visual Studio, and that will work without even you implementing this one. You don't have to put this above the main or below the main or whatever you want. No. You can just take this code, but you need to include C string. You need to include C string for strlen to work. Okay. So here it is. Here it is again with only CPTR of I. As I said, you can abandon not equal the \0 because it's when that is \0. This is a 0. This is a 0 because the ASCII for this \0 is a 0. And that false goes out. That's it. So you can use it with an array in the heap using a pointer, or you can use it with an array in the stack without pointers, or with the pointers but without the new, if you want, without the new command. Okay, now passing arrays to functions, you can do it the way we have done things with arrays. You can use a pointer, or you can use an array with those square brackets or with a pointer. Both will work. Now we have a function that is strcpy, string copy for strings. So string library, the one you should include to use these functions, has a function for copying one string to another. Here is the function prototype. It returns a character pointer, and it's called strcpy. It takes two things. You give it the pointer to the array, the character array you want to store to, you want to copy to, and the one you want to copy from. The C string you're copying from, and the C string you're copying to. So it copies from the source to the destination and returns a pointer to the destination. So if you were in my class, I would ask you to work with your neighbor to write this function and to find a way to write a function that will copy from the source to the destination. Since this is an online class and I'm recording this video, I'm going to ask you to pause this video for 5 minutes and try to come up with an implementation to a function like this that copies from the source to the destination and returns a pointer to the destination. Go work on this and come back. Okay, assuming you found a way to do it, here is how we are going to use your function, the one you just thought of. We are going to have original, and by the way, if you use strcpy or strSCP or any of the C string functions, it's going to give you a warning. To get rid of this warning, follow these instructions. This is what this slide is all about. You don't have to do it actually. Okay, the way we are going to use the function you just implemented, the strcpy, is here is original C string, a character array, which is a C string, a copy C string, both are 80 character worth of elements or size. So it doesn't have to be 80 elements for the word. You can just have ABC. Doesn't matter, as long as wherever you stop, you place a null terminator because it's needed. So please type a word less than 80 characters, right? Less than 80 characters. So we print original, and then we print the result. Basically, the pointer comes back from strcpy, and this is going to copy the original to copy. Or we can just use this, strcpy, copy and original, and then we print copy, like cout copy. Same way. Or we can use it this way. We have original, we are not asking the user for it, we type it in, hello there, and we use copy. And when you copy this code, you might need to replace those quotes because the Visual Studio is not going to recognize them, same as these. So here is how the strcpy is implemented. So character asterisk strcpy, that takes two pointers, the destination and constant to resource, because the source is not to be changed, right? So we want it to be constant. And then we're creating a pointer copy to the destination. this is the one we are going to return. And we say, okay, copy the value that source is pointing at to the destination. And if the result of this one is not equal to the null terminator, advance the destination and the source, and that goes on. So A, B, C, and the null terminator. This is this is the original, right, or the source, and the destination is going to be copying A, B, C, and when it's null terminator, it's just going to add the null terminator. Now, the reason that works is that those two, so that is going to copy A, B, C, and null terminator, right? So the reason that works is that those two are copies of original and copy, and copies of original and copy if used for these examples, right? So dist and source are copies. This is why it works. If you tried something like this, character original array, this is character array original, hello there, and copy. If you try to do it in your main, like while copy plus plus dereferenced equal original plus plus dereferenced, this is not going to work because you're trying to advance the actual variables, original and copy. If you made copies of these, like a new pointers, and you worked on the new pointers, this is going to be okay. Because why is this going to throw you an error? Because you're asking the compiler to participate in ruining the two arrays. What do I mean by ruining the two arrays? Because you're advancing the actual pointers, copy and original, if you're thinking of these two as pointers, right? So basically, you cannot use original and copy. You have them in there. The operating system is thinking that you're using them, but you don't have actually access to them, because eventually here is your array, here is your two things, here is the copy and here is the original. So you keep advancing that and copying, right? Keep advancing and then copying. Then eventually original is going to, after it's being advanced, it's going to point at what's out, and this is going to be advanced at in here. And those are not valid indexes unless you then said, okay, I'm going to reset them, and this is a long way. But the compiler is not going to actually participate in ruining. When I say ruining, but I mean participating in not having access to the memory locations in here, because you want. So how that is actually happening, how is that going to happen? I'm going to show you why it's going to copy everything. It's basically what we did before when we have the function that duplicate the copy, make a copy of the pointer passed, and basically the operator plus plus, right? So making a copy of the parameter passed, the pointer passed, then advance the pointer the size of the data type, in this case character. In the previous example I gave you, that was int, and then returned copy, right? Return copy. So if I have A, B, C, and then /0, I have dist is pointing at this one. This is dist, and this is source. Let's just, for abbreviations, let's just call this source src. Source. Both are pointing to the first locations of each array, right? Now we are saying assign where the source pointing at to the destination, which is copy A. Then advance both. Then B. Advance both using those. So advance both. So C. Then you're copying the \0, then advance, then the final thing is going to be in here, right? This is where you advance things. So basically those are not going to be advanced eventually, because when that happens, you store the \0 in here, and the result of this one is the result of the assignment, right? The result of the assignment, which is a 0. Is it equal to \0? Yes. So do not advance this one. Do not advance this and source. So basically it's just going to be pointing at here. But we don't care because we are just returning start. Start is still pointing at, it's still pointing at A. So this is what we are turning, A. You just need to do it slowly and then you'll understand everything. And again, if you have only 2 pointers, just the original pointer to the original and the original pointer to copy, and you're trying to advance them like this, the compiler is not going to participate in such thing. If you're making copies of them and you're advancing the copies, that's fine. When you pass the addresses, you still have the original things, like in here, this one and this one, pointing at the locations of that array. So advancing those things doesn't matter that much, because those are just copies. Okay, so would the following work? Character original array, hello, copy, and I use strcpy on copy and original. Will that work? Now the answer to that is no, big no, because original is not null terminated. But do not confuse this when you assign the character array with a string in double quotes with this. Because when you do this, the compiler immediately adds \0 without you knowing, without showing you that it's added. But when you deal with character at a time in an array, you must manually add the \0 for it to work, to be considered a C string. This is a C string, this is not, unless you added a \0. Okay? So, other functions in C string, you can use other functions in C string, a lot of functions. There are many other functions in C strings you can use. C string is a null terminated character array. Library functions needed the null terminator to work. The C++ programming book we are using, if you go to section 8.1, functions on page 461, those are many functions, or you can go to creferences.com or c++.com/reference or references. These are places you can find functions, or Google C string functions. it's going to show you those functions. So library functions do not do error checking for null terminator. So you must make sure that your C string is ending with a null terminator. If you use it in a string like this, it's automatically added. If you use it this way, it's not automatically added. So for C string functions, you must include C string library. So pointer arithmetic and arrays, this is the last thing we are going to talk about in this lecture. We can also use comparison, comparing pointers using these operators. So you can say which one is advanced, which one is ahead of the other. Is pointer 2 greater than or equal PDR? Pointer 2 is pointing at this point and PDR is pointing at this one. This is true. If we are saying, for example, less than, this is false. If we're saying those are pointing to the same location, equal, this is false, and so on. So one more practice activity with pointers and C strings for you to practice. So your task is to write the reverse function using pointers to reverse a C string, character asterisk reverse. Here's the prototype of your function, and here's something you can try, and then reverse. So because your function reverse, returning a pointer to the reversed C string, that would print, for example, 6, 5, 4, 3, 2, 1. So turn off your screen that has the Visual Studio, whether it's 2015, 2017, or now we are using 2019. Think about it and then implement the function. So then you can test your function, the one you implemented after you came back, on this. So you can copy to your main. You can copy this to your main. And for this one, it's just going to reverse 1, 2, 3, 4, 5. It's going to swap 1 with 5, 2 with 4, and not swapping 3. Same thing in here. 1 with 2, 2 with 3, 1 with 4, 2 with 3, and that's it. And with 1, it's just not doing anything, not swapping. And for the empty thing, it's not swapping anything. So here it is, and let's see what your function looks like. So work on that function and come back. So write a function that reverses a C string. Okay, assuming you thought of that and you did it, here is a possible answer. So here is the swap function that you would need to swap two characters. Here's an character pointer, another character pointer, and you're using the empty cup replacement or swapping. Remember that empty variable. So here's a temporary variable that you have the value of pointer 1 inside, the value that pointer 1 is pointing at inside, and then pointer 1 now can receive the value of pointer 2, or what pointer 2 is pointing at. Then pointer 2 now pointing at something that reusable, and you put C, and that's it. You know that from previous lectures. What we are mostly interested in is this function, the reverse function. The reverse function that takes a C string and returns a character pointer. So we are saying we are reversing this one. So you can abandon every C out in here. Doesn't matter. What we mostly interested in is how you do it. So int length. So we are storing the length. We use the strlen function from C string library. And now we have the length. And we say for int I equals 0, I less than the length divided by 2. Now you can have parentheses in here or not, doesn't matter, because it's going to be executed before the comparison. So length divided by 2. If I have 1, 2, 3, 4, 5. What is the length of this one? It's 5, right? And when I say length divided by 2, this is 5 divided by 2. Int divided by int gives me int. So that gives me 2. I go from 0 to less than 2. 0 to less than 2. So I'm going to be 0 with 1. And I'm going to swap C string of I, so 1, with C string of length 5 minus current I 0 minus 1 with 4. 0, 1, 2, 3, 4. These are the indexes. I'm swapping 1 with 5. So the first iteration is going to produce this 5, 2, 3, 4, and 1. The next iteration, I becomes 1, right? So that is C string of 1, and here's 1. Length is still 5, so here's 1. And this becomes 5 minus 1, this is 3. So I'm replacing, and since this is not constant, I'm actually modifying the original value. So at 1, this one, and this one, 3. 0, 1, 2, 3. So I'm dealing with these two. So the next iteration is going to be 5, and swapping those, 4, 3, 2, 1. And that's it. It's swapped, right? Same thing if it's not odd length. If it's like 1, 2, 3, 4. It's going to swap 1 with 4, 2 with 3, and so on. And that's it for this lecture. So with pointers, we have seen how to create pointers, how to use them, how to use the dereferencing, the ampersand, the address of. We used null pointers. We used the indexing, square brackets. We use plus plus, and same way you can use minus minus. The incrementing and decrementing, new, delete. We had a look at C strings, null pointers, null terminators, strlen, strcpy, which is string copy, string length, and so on. That's it for today, and have a great day.